Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 3, part of this playlist that I'm calling Continuous Random Variables. Let's jump to today's topic, which is the exponential distribution. Now, it's a particular case of the gamma distribution, which we covered in the previous video. It's a continuous analog of the geometric distribution. It also has the key property of being memoryless. The exponential distribution is the probability distribution of the time between events in a Poisson process, i.e. a process in which events occur continuously and independently at a constant average rate. Now, the definition of exponential distribution: let x be an exponential random variable with parameter beta greater than 0. Then the density for x is given by f of x is beta e to the minus beta x. This is for all x greater than 0. There is another parameterization where they use the, instead of the scale parameterization, they call it a rate parameterization. So it's 1 over beta. So they just move beta to the denominator in each of these cases. We're going to use this form for this video. Both are equally used. Now let x be an exponential random variable with parameter beta. The mean and variance and moment generating function of x are given by, the mean is 1 over beta, the variance is 1 over beta squared, the moment generating function is beta divided by beta minus t, and the proof is very short. See the video on gamma distribution, which is the one before this one in the playlist, Introduction to Mathematical Statistics, and let alpha equal 1, and these results follow. Let x be an exponential random variable with parameter beta. Then the cumulative distribution function and the survivor function of x are given by these two expressions. F of x, which is the probability that x is less than or equal to some number, is 1 minus e to the minus beta x. The survivor function is 1 minus that, which is the probability that x is greater than some value, which is e to the minus beta x. Here's a quick proof. Let f of x, by definition, equal x less than or equal to x. That means we integrate the density, which is an exponential density, from 0 to x. The antiderivative of that is this. We evaluated x and 0. Then you get minus this evaluated at x, and then you get minus, then evaluated at 0, and it's minus 1, so minus and minus cancels. We get 1 minus e to the minus beta x. Now, the survivor function, which is probably x greater than some number little x, is 1 minus CDF, which is e to the minus beta. Let x be an exponential random variable with parameter beta. Then x possesses the memoryless property, which we'll define it as this. Probability that x is greater than or equal to t plus h, given that x is greater than or equal to t. That's just equal to the probability that x is greater than t. So you can ignore the t part. This is for x greater than or equal to t. So the proof is this. This conditional probability is, by definition, this. So the numerator is the intersection of these two events. The intersection of x being greater than t and x being greater than or equal to t is just that x is greater than or equal to t. But these are the survivor functions. Remember, you might say, well, but there's an equal sign. But since it's a continuous random variable, probability of a point is 0. So it actually doesn't add to that. So this is the survivor function of these values. And then we get cancelizations, e to the minus bh. Well, that is the probability that x is greater than or equal to h, and that's what we wanted to show. Let x1 through xn be independent exponential random variables with parameter beta that form a random sample. Then the distribution of y1, which will be the minimum of these values, is an exponential distribution with parameter n times beta. Now let's prove that. Now the technique we're going to use, we developed in one of our previous videos, that if we take the derivative of the CDF, we get the density. And that's the approach that we're going to use here. So let's first find the CDF. So f of y1 is 1 minus the survivor function of that, which is 1 minus the probability that y1 is greater than some value. Now, since y1 is the minimum of these x's, that says that x1 has to be greater than y, x2 has to be greater than y, all the way to the xn has to be greater than y. And since they're independent, it's the product of these values. Well, since the x's are an exponential random variable, we know, and it's a survivor function, we know that value is e to the minus beta y for each of those. And the product there's n of them, so it's going to be e to the minus n beta y. Now we take the derivative of that to find the density. So the density of y is the derivative of the CDF, and that constant goes away. The minus comes out front and actually should cancel with that. So that minus should not be there. I'll take it out in the hard copy. So we have n beta, e to the n beta y. And so this is an exponential distribution with parameter n beta. Well, that's what we wanted to show. Again, that should be a plus. Next theorem, consider a Poisson process with parameter lambda. Now I'm going to point you back to a video I have on the Poisson process. Let t denote the time to the first event. Then t has an exponential distribution with parameter beta equaling to lambda. Now here's the proof. Let x be a Poisson random variable with parameter t lambda, where t lambda is the mean number of occurrences in the interval 0 to t. Now here's the thing. Lambda is the mean number of events in a unit interval time, but we want it for some generic some interval 0 to t. So we have to take t times lambda to find the mean number of events in this interval. So we're going to find the CDF of t and then take its derivative to find the density. So the CDF is 1 minus the survival function. So it's 1 minus probability that t is greater than, this value t. It has to be, we're outside of that. But in order for the first event, remember t is the first event, to be greater than t, it means that the Poisson process has 0 events in that interval. So 1 minus probability that x is 0, and that's a Poisson process, which we know. Just plug in 0 for x, we get 1 minus e to the minus t lambda. Now when we take the derivative, we find the density. So f of t is the derivative of this CDF, which here it's going to be, and it's with respect to t, so it's going to be lambda e to the minus t lambda. But if we let lambda, so I wish I'd have put that step right here, and if we let lambda equal beta, then it's an exponential distribution. And that's what we said. When beta is equal to lambda, then it's an exponential distribution. So let's do an example. Accidents on a certain stretch of I-70 occur according to a Poisson process with an average of 3 every 2 hours. What is the probability that the first accident after midnight occurs between 2 and 3 a.m.? Here's the solution. Let x be an exponential random variable with parameter beta equal to 3 over 2. Now notice that in the setup it says 3 every 2 hours. So that's the unit measurement is every 2 hours. So we have to knock it back to just 1 hour. So that's going to be 1.5 every hour. And that's what this is. So we take the integral from 2 to 3, right? From 2 to 3 of an exponential distribution with beta equal to 3 over 2. So the integral of from 2 to 3 of this exponential distribution, take the antiderivative, you get minus e to the 3x over 2. Substitute in 3 and 2, you get e to the minus 9 over 2 plus e to the 3, which is this value here, e, 0.0386, da 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 da. That's the answer. Now we're going to do an R illustration of this. We're going to solve it 3 different ways, and you'll find it interesting. First approach, we're going to use a Poisson process to solve it. And then the next, of course, the exponential distribution. So here, remember the problem is set up that 3 every 2 hours. But we can easily see that every hour it's 1.5. And if we're looking from midnight to 3 a.m., it means we want 0 events from midnight to 1, 0 events from 1 to 2, and then at least 1 from 2 to 3. So if we set up the Poisson, the d Poisson is the density of a Poisson evaluated at 0, and the mean, lambda, is 3 over 2. So that represents midnight to 1. This is 1 to 2, and then 1 minus 0 is at least 1 event occurs in, from 2 to 3. Take that product, and it's the same, 0.038, da 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 da. We got the right answer. So let's solve it using the CDF function of an exponential distribution. So P, which is the CDF part of the exponential, we go from 0 to 3, that's the CDF part. Beta is 3 over 2 minus the exponential from, the CDF of the exponential evaluated at 2. Of course, beta is 3 over 2. We get the same quantity. Let's do a quick simulation of 1 million reps. Let's take a sample size of 1 million from an exponential distribution with beta equal to 3 over 2. Let's find how many times we're over 2 and under 3. Add up those times. Divide by the 1 million reps. We get 0.0388, which is really close to theoretical. All right, we're at 12 minutes, so I need to stop. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.